Hello everyone, welcome to Amateur Hour number 10. Wait, 10? Party time! We reached double digits, baby! We're of course going to be continuing lecture number 3, which was about sorting algorithms, and I believe that the professor was going to start talking about data structures now, so let's get on with it. On to the show. But before we start listening to our professor again, I wanted to reiterate what we learned in the first part of lecture number 3. He did talk about how efficient algorithms should use very little time to come to an answer, and they also should try to not use too much memory to get to that answer. Then he also talked about 3 different sort of ladders. Big O was the runtime, the upper bound of how many steps could be taken to come to the correct answer. Then there was of course the omega, which was the lower bound on the runtime of your algorithm, and there was theta, which was a sort of holy grail of algorithms, which was when your lower bound and upper bound are the same. And then the professor also talked about 2 different types of search algorithms, which were binary search and linear search, and it goes over each element in your array one by one until it finds the element it's looking for. So linear search will go linearly through your data until it finds the element you're looking for. And then there was binary search. It needs a sorted set of data, and then it will go to the middle element of your data and check, should I go to the higher half or the lower half? And then it will try to halve the remaining set every time it goes into a search until it finds the element it's looking for. And then last up, we're also going to be using string compare to compare 2 strings, and this came from the help site. Those were the most important parts of lecture number 3, part 1. And then we're going to start lecture number 3, part 2 now. The professor just talked about how we can define our own data type if we want to, and we'll have to use typedef struct. And then we'll just have to say the data type we're having will always have a string name and it will always have a string number. But this could of course be other types of things. And then in the end you define what you want the name of the data type to be. So we have now made a data type called person, and person will always have a name and will always have a number. He's actually quite often using volunteers, and I expect that many people find it quite daunting to go up on stage. I mean, these lectures are watched by, what is it for this one? Yeah, this lecture has been viewed 160,000 times, so getting up on stage there is actually, I guess, it's quite nerve-wracking, even if you're going to do something very simple. He said that it's not efficient to move everyone up 1 and then place the 0 at position number 1. Rather, the audience suggests maybe instead of moving everyone, we could just swap 0 and number 5, which is currently at number 1. Looks like our sorting algorithm suggested by the audience was not that efficient. I have not counted, but it looked like the second way of if the one is higher than the other, swap them, was faster. The professor just proposed that the total amount of steps needed to sort using a selection sort equal to, well, first you're going through each element once, and then you know for sure that one of the elements is in the right place, so you're not going to look at that element anymore, so you're going over n-1, then you know 2 elements are in the right place, so you're going over n-2, and then you're continuing that until you have only 1 element left, and then you know that the amount of times you go over each element is n times n plus 1 divided by 2. As long as your n gets extremely large, then your amount of steps to go through your set and sort it this way is extremely large as well, because the n squared is going to make your amount of steps enormous. So that's interesting. Last time I said that when your theta, your upper bound and your lower bound are the same, then you found the Holy Grail. But in this case, the lower bound of the amount of times you go over your data is n squared, because first you're going over all 8 and you're going over all 7, all 6, all 5, all 4. So the only thing that matters for your upper bound and lower bound is the size of n, which means that the upper bound and lower bound are the same. But I'm not going to say that this way of sorting is the Holy Grail.
He chose poorly.
And now he's giving us some pseudocode for the bubble sorting, which was comparing two elements and then putting those two elements in the right order. It looks like we're going to end up with an n squared this time as well, even with the bubble sort. So the upper bound on the runtime is n squared again. The upper bound on the runtime is going to be the same, but the lower bound this time is going to be different. We're looking for a sorting algorithm that is faster than n squared. Okay. Recursion is a technique whereby a function calls itself. Okay. I know what those words mean, but I don't understand them yet.
Did you get any of that?
It looks like if you're using a recursion, you're very often also going to need an exit to that recursion. Aha, so he did the sorting and then he compared the first element of one list to the first element of the other list. And then he put the lowest one at the start of a new list. And then he kept on, okay, so we have maybe a new element on the first list compared to what we had before. Okay, is this new first element the lower of the two elements? No, the one on the right is. Okay, we put the one on the right at the left. And then we kept going until there was nothing left. Okay, so now he of course has shown us the merge sort method, and I'm starting to understand it. I'm just not fully envisioning how it entirely works. I think I'm going to have to practice with it before I truly, fully, 100% understand it, but I am getting a grasp for it. No matter how your set is already sorted, even if some elements are in the right position, you will always use n times log n to sort your set in both the upper bound and the lower bound. So your theta is of course n times log n, because they are the same. So this merge sorting, if your set is already or often already in the right order, is not that efficient, but otherwise it is. I have to say that by now I do get how it works, but I really wouldn't know how to code this. So which do you think will be the slowest? Well, selection, merge, or bubble sort? Well, it looks like merge is already done, so that's not the slowest. I'm going to guess that selection sort is the slowest of these. It looks like we have about 50 elements, I don't know. So yeah, selection sort, that's my guess. Oh.
Lose! Good day, sir!
Yeah, it was bubble sort. And I guess that was it for the algorithms of this week. We're going to be practicing, of course, with the assignments from lecture number 3 between this and the next amateur hour, and I think we'll make a video about the assignments as well. I hope to, of course, see you in either that assignment video or the next amateur hour. See you around!